Morning, Year 12. We're going to look at a couple of things today. The first is oxidation of alcohols. It's quite a small little topic, and it's very highly repetitive. So you just got to learn sort of just two patterns really, and that covers the oxidation of alcohols topic. So it comes up quite a lot. Not normally as a question entirely on its own, but it will be part of lots of other topics, including the test tube reactions, which we'll have a look at later. So the oxidation of alcohols, we're going to take the three different classes of alcohols. So our primary, we've got our secondary, and our tertiary alcohols. And we're going to try and oxidize them. So this links to your redox topic. And the oxidant we need is quite a powerful oxidizing agent. These are not very powerful reducing agents. It's relatively difficult to oxidize them. And so we use potassium dichromate. So it's K2Cr2O7. Now this on its own doesn't work. It needs to be acidified. So we call it acidified. Now if you miss out that bit, the acidified, you will lose marks. Like you will lose at least 1, maybe 2 marks for it. It's acidified using sulfuric acid. So the way you can write it is acidified potassium dichromate, or K2Cr2O7. You can write H plus Cr2O7. Sorry, that should have the K2 in front there. Or you can have H2SO4 slash K2Cr2O7. So those are the three kind of ways you could represent it. You can also write this out as potassium dichromate. Now, this chemical, when you do the practicals that involve it, which there are 2 of them, so there's the test tube reactions practical, and one where you're going to do the oxidation of an alcohol. You will see that this has a very bright orange colour. So it's an orange, and it's chromium 7, or was it chromium 5? 1 second. So we've got +2. Okay, it's plus 6. So we've got chromium 6, and it's got a very orange colour to it. So that's how you'll recognise that when you use it. It's a very dangerous chemical to use, so you've got to be very cautious, as the mixture is highly corrosive, powerfully oxidising, and it's highly toxic. So it's one of the most dangerous things you'll use in A level. Now this is going to change colour, which is how we use this as a test tube reaction for the presence of alcohols. Now the primary alcohol, if we take the primary alcohol, when we oxidise it, so we use our oxidising agent. Now we often represent that as just a sort of brackets with an O. We form an aldehyde. So you see I've maintained the same number of carbons, so I've gone from 2 carbons to the 2 carbon aldehyde. It removes 2 hydrogens from the molecule. So if we do the formula for this is C2H5OH versus C2H4O. So we've got 6 hydrogens in total on the left, only 4 on the right. So we've removed H2 from the molecule. Sort of, if we go the other way, if you add H2 to a molecule, which we call a hydrogenation, that's also a reduction of the molecule as well. And so if you go to university and stuff, you'll see about the reduction of things going the other way, so moving going from right to left by adding hydrogen to the molecule. And actually that is covered in Year 13 actually as well. So we get to the aldehyde, but this can also be oxidized as well, and actually it's more susceptible to oxidation than the alcohol is. It's more reactive than the alcohol, and so if you just leave that in there, it will get oxidized again by another equivalent of our oxidizing agent, and we form the carboxylic acid. So we go from ethanol to ethanal to ethanoic acid. So we've got C2H4O2. So we've added an oxygen in this time rather than removing hydrogen. So we'll come back to sort of how we might play around with this more precisely, but we go through in these 2 steps. So it's 2 separate oxidations. So that's what we do for primary alcohols. For secondary alcohols, so we start with our propan-2-ol. we go through the same steps. So we essentially turn this into a CO double bond where the OH group previously was. So it goes through an oxidation, and we get to propanone. Now this can't be oxidized any further. You can't sort of add in an extra OH, which is what we've sort of done here. We've sort of like slotted in an O between the C and the H from start to finish. There is no CH bond there, so we can't oxidize this any further. So this reaction doesn't proceed any further. Now the tertiary alcohols, we simply cannot oxidize them. They're resistant to oxidation. So these oxidative conditions, so with potassium dichromate, it doesn't proceed, the reaction doesn't occur. So these aren't susceptible to oxidation by acidified potassium dichromate. The oxidation they are susceptible to is combustion. So you could burn these, that would be an oxidation to form carbon dioxide and water, but it won't be oxidized by acidified potassium dichromate. So we've run over the sort of rules for what's produced by the oxidation of the alcohols. You now need to be able to write the overall equations for the reactions. So be asked to write sort of a single line showing the formula or the equation for this reaction. So we start with the primary one. This is the most difficult one to do. So we'll take our example from earlier. So we've got ethanol, and it's oxidized to ethanal, and then the ethanal can be oxidized to the carboxylic acid. So if we start with our CH3CH2OH, so we write in our oxidizing agent as bracket O. We don't write in K2Cr2O7. That reacts, and we sort of remove sort of the two hydrogens from the molecule. So one of these, and this hydrogen and this hydrogen, roughly speaking, and to form our ethanal. So we get CH3CHO. So you should remember we represent the aldehyde group by CHO rather than COH. Now the oxygen takes with those two hydrogens and forms a molecule of water. Now in the second step, we take the aldehyde that again reacts with the oxidizing agent, but we don't remove hydrogens this time. We sort of add the oxygen into the molecule to form the carboxylic acid. So we go to CH3COOH, and there's no H2O produced by it. Now this isn't the overall equation. These are in two steps for going from ethanol to ethanoic acid, right from the primary alcohol to the acid. You need to be able to combine those together, and so it's a skill that you will kind of come across occasionally in your A-level chemistry. So what we're going to do is we're going to add both sides of the equation to each other. So I'm going to add both left-hand sides to each other. So I've got CH3CH2OH plus brackets O. And I'm going to treat it very much like I would an algebraic expression in maths. So these two O's are together, so we've got plus 2 brackets O. And if we notice, we've got the aldehyde on both sides of the reaction. So just as you might if you had X on both sides of an equal sign, you just cancel them out. We can cancel them out. It's an intermediate if we're going all the way from ethanol to ethanoic acid, and so it doesn't appear in our overall equation. So that leaves us with the CH with the alcohols formula here, plus the 2 oxygens. That leaves us just with our ethanoic acid and only 1 water molecule. So that is our overall equation for the oxidation of the alcohol to ethanoic acid. Now for the secondary alcohol, it's a one step, so it's much simpler. We just need to basically write out what we see. So we've got CH3CHOH, that reacts with 1 equivalent of our oxidizing agent, produces our propanol, not propanol, but propanone. I'm going to put that in the brackets. I don't think it's entirely necessary though. And that the O does gain, it removes 2 hydrogens, removes this and this hydrogen, leaving us with a water molecule. So that one's nice and simple. With the tertiary alcohol, no such thing takes place. Now we're going to consider, with the oxidation of the primary alcohol, how we can select which product we produce. And the way we're going to do that is by considering the boiling points of these different molecules. So ethanol has a boiling point, I think it's around 78 degrees Celsius. The ethanoic acid, it's about the same. Off the top of my head, I think it's also around 78 degrees Celsius. Maybe the ethanol is 76. But the aldehyde, it's somewhere in the region of 30 degrees Celsius. It's much lower. It's a much more volatile chemical, and that's because these two have got hydrogen bonds, whereas this one only has dipole interactions. So we can change our practical setup to select which one we're going to form. So there's 2 different ways, 2 different setups. We have heating under reflux,